In this video, we're going to take a look at another application of first-order differential equations, and this is mixture problems. So the idea is you've got some sort of container, and that container has a mixture of stuff in it, like water and salt, let's say. And you know how much salt there is, and then you also know that stuff is being poured in and stuff is being poured out. And there's the question of how much stuff is in there at any time. So here we go. The main equation that we're looking at is essentially the rate of change in the amount of stuff is the rate that it's coming in minus the rate that it's going out. So here's an example, right? I've got a tank that initially contains 1,000 gallons of water. And in that water is dissolved 10 pounds of some pollutant. I don't know what it is. It doesn't really matter. Now, I am going to be dumping other stuff into this tank and taking stuff out. So we've got 0.2 pounds, we got water coming in, but the water is contaminated coming in. It's coming in at, it's got 0.2 pounds of pollutant per gallon and is being dumped into the tank at a rate of 5 gallons per minute. Okay. At the same time, we have water and pollutant being drained from the tank at a rate of 5 gallons per minute. Okay. Find a function that describes the amount of pollutant in the tank at any time. Okay, so here we go. I'm going to let y be the pounds of pollutant in the tank. Okay. Now, in these problems, sometimes you're asked to find concentration, sometimes you're asked to find amount of stuff. But when you're doing the calculation, you want to deal in amount of stuff, not in concentration. The thing is, concentration is it involves two things, like amount of salt and amount of water. And if you change either one of those, you change the concentration. I want to focus just on the amount of pollutant that's in this tank, not the concentration of that, but the amount. So I'm going to let y be the pounds of pollutant in the tank. And I'm very careful when I do these problems that I make sure I know what my labels are. That y is being measured in pounds of pollutant. Okay? And because I'm told that initially there's 10 pounds in the tank, then I know that I have this initial condition at time 0, y is equal to 10. Now, information we're given is about rates, and there's a couple of different types of rates here. Concentration is a rate, right? This 2 pounds of pollutant per gallon is a rate of pollutant per gallon of water. But then there's also the rate at which it's coming in, 5 gallons per minute. Okay. Now, notice I'm going to be very careful with the labels because the labels help me to get the differential equation right. Okay. We're given information about rate in and rate out. So here we go. dy dt, if y is the amount of number of pounds, then dy dt is the rate of change in the pounds in y. Per minute. Pounds per minute is what this dy dt is going to be. So I got to make sure that everything here is going to be measured in pounds per minute. Okay. So dy dt, the rate of change in pounds per minute, is equal to the rate coming in minus the rate going out. Now what's coming in? Coming in is 0.2 pounds per gallon. Now that's not pounds per minute, that's pounds per gallon. So then I have to multiply that by gallons per minute. And it's coming in at 5 gallons per minute. That's right there. So this 0.2 pounds per gallon times 5 gallons per minute. That's the rate coming in pounds per gallon. No, in pounds per minute. This was pounds per minute. This is pounds per minute. The gallons cancel out. Likewise, now, what's going out? Well, all they tell me about what's going out is that it's going out at 5 gallons per minute. So I know that's 5 gallons per minute. But how many pounds per gallon? What's the concentration? Well, the concentration is going to be changing. I mean, initially the concentration you can see is 10 pounds per 1,000 gallons. So it would be 0.01 pounds per gallon, right? But it's coming in at a different at 0.2 pounds per gallon. So the concentration should be changing because the stuff coming in doesn't have the same concentration of what's already in there. So what I have to do is I've got to come up with a function that's describing the concentration at any time. Well, the concentration at any time is going to be the amount of pollutant divided by the amount of water. Well, since you're pumping water in at 5 gallons per minute and out at 5 gallons per minute, the amount of water is the same. It's 1,000 gallons all the time. So the concentration is right here, however many pounds you have, which that's what Y is measuring, it's pounds of pollutant in there, and then divide by the 1,000 gallons of water. So this would be the concentration at any time, and that stuff is being pumped out at 5 gallons per minute. So again, the gallons cancel out, and we're looking at pounds of pollutant per gallon. No, why do I keep saying that? Pounds per minute. Right? That's the whole thing. Pounds per minute, pounds per minute, pounds per minute. Everything is right in, right out. The total rate is in pounds per minute. Okay. So now simplifying that equation, and getting rid of all the labels just so that we can see the numbers here, I got dy dt equals 1 minus 0.005 y. This is both first order linear or separable. You can do it either way. I'm going to choose to do it as a separable differential equation. So I'm going to divide everything by the left-hand side here and multiply both sides by dt to end up with this. And then integrate both sides. The integral of dt, of course, is just t plus a constant. This side right here has a u substitution with u equals the denominator. Du then is minus 0.005 dy. So I don't have the 0.005, the minus 0.005 over here, so that's why I end up with the minus 1 over that. And then I get a 1 over u du, which is the natural log of the absolute value of that stuff. And multiplying both sides by the negative 0.005. I'm not worrying about the plus c because negative 0.005 times c is just some other constant. Okay. And then exponentiate both sides and do the same thing we've done several times already, where the e to this thing is e to the first part times e to the c, and e to the c is a positive constant, but c over here is a positive or negative constant. And I can get rid of the absolute value signs. And then solving for y, so I subtract the 1 and then divide by 0.005. And the 1 divided by 0.005 is 200. And the negative becomes positive. Again, this c now should really be a c divided by that negative 0.005, but that's still a different constant. At this point, I can, what am I doing? I can plug in initial conditions and figure out what c is. So at time 0, plugging in a 0 for that t there, y is 10, so plugging in 10 for that y and solve, and I see that y is c is minus 190, and so my function is, at any time, the amount of pounds of pollutant in the tank is 200 minus 190 e to the minus 0.05t. The graph of that thing looks like this. Notice that at time 0, it's there at 10, and then it increases. The amount of stuff increases. That makes sense that it's increasing. So looking back up at the original problem, the initial concentration was, what do we say, 0.1 gallons, well, 0.1 pounds per gallon, and I'm putting in 0.2 pounds per gallon. So yeah, it should be going up. The concentration of the water coming in is more than the concentration. Actually, this is 0.01 pounds per gallon to start with, and it's coming in at 0.2. So substantially more polluted water is being dumped in, right? So yeah, we would expect it to go up. In fact, in the end, this has a horizontal asymptote of 200, which, notice, the concentration of 0.2 times the 1,000 gallons in the tank would say, hey, you should be expecting to end up with about 200 gallons in the tank over time, 200 pounds in that 1,000-gallon tank over time. And that's what's happening at a horizontal asymptote of 200. So now I want to look at two variations of this problem. One is I'm going to change the concentration of the water coming in so that it's less than what was initially in the tank, and see that in that case we should be expecting the amount of pollutant to be going down. And then I want to do one where the rate in is 5 gallons per minute in. I want to do 6 gallons per minute out so that there's a different amount of water in the tank at different times. So I'm going to do those next, but in the next video.